So it's my pleasure to introduce Nicolas Blanco, who will be talking to us about generalization of multi-categories and their string diagrams. Take it away, Nicolas.
Yeah, thank you. And so thank you all for coming to the talk, and thanks to the organizer for giving me this opportunity. So I'm a PhD student at the University of Birmingham, just writing up under the supervision of Noam Zellberger, and I will be talking to you about my work, which is on multi-categories, the string diagrams, and how to generalize them. Let me start with some kind of introduction about multi-categories. So they've been introduced by Lambeck in I think 69 paper, Deductive Systems and Categories. So they were already around before, but I think it's the first time somebody put it on paper and give it the name multi-categories. And so there are generalization of categories where morphism has multiple inputs. So you can keep in mind vector spaces and multilinear maps. So you have this idea of a map having many inputs and one output. You can also think of colored operods. So if you know operods, multi-categories are just colored or multi-sorted operods. Well, for me, an operod is set-based, so it's not topological. They give models of intrinsic multiplicative linear logic and can also be used to describe algebraic theories, like generalizing the notion of Liouville theories. And also they're nice to study monoids. So monoids live naturally internal to any multi-category, which generalize the notion of monoid internal to a monodal category. And when I say they live naturally there, what I mean is that they are global elements in some sense for multi-categories. So it's a nice setting to look at monoids. And what will be interesting for us today is that you have a notion of tensor product in a multi-category that is defined with a universal property. So the tensor product is defined uniquely up to unique isomorphism. So it's exactly the same idea that what you do in a vector space, where you say that the tensor product is uniquely determined by the fact that it's linearizing any multilinear map. So we'll do the same thing, but for any multi-categories. And so they gave a different perspective on tensor product than monodal categories. So multi-categories with tensor product are the same, so they are equivalent to monodal categories, and you have even two equivalents of some categories there. But they have a different flavor, where the tensor product is uniquely determined by the structure, while in monodal categories, it's some extra structure that you put on your category. And so in this talk, I will first talk about multi-categories, the notion of representable multi-categories, multi-categories with tensor products, and their string diagram. And then I will look at three different ways of generalizing multi-categories. One is polycategories that has been introduced by one of Lambeck's students, Chabot, in the 70s, if I remember correctly. And so there are generalization where the morphism now also have many outputs. And so you have this idea that representable polycategories are related to star autonomous categories, which are models of linear logic, but classical linear logic, not intuitionistic. And they've been so all of these have been studied first by Barr for star autonomous categories, and then Canadians category theorists, Coquette, Seeley, and Blut for the connection with polycategories. Then another way of generalizing multi-categories are virtual double categories that has been, for example, introduced in Leicester under the name of FC multi-categories. And well, the idea is that a virtual double category can be seen as a colored multi-category. And you have now a notion of representable virtual double categories that is related to double categories. And so the string diagrams have been used, for example, by David J. Meyers in this paper in 2020. And then I will talk about functors of multi-categories. And my vision and idea of functors is inspired by some work by Paul-André Méliès and Noam Zellberger, where they think of functors as type refinement system. So I won't go into the details of that, but it's kind of in the background of how I think about these things. And in particular, you have a notion of push forward that lets you define a vibration of multi-categories. And push forward can be thought as parameterized notion of tensor product. And in particular, multi-categories that are up-fibered over the terminal one will correspond to representable multi-categories, which is a result by Claudio Armida. So this is ambitious. This is a lot of things. So probably won't have time to go in details on everything there. So let me first stop for some question. And if one of these really talks to you and you want to learn more about virtual double categories and not so much about polycategories, for example, let me know just now so that I can kind of reorder the talk and start with virtual double categories or functors. So I guess I will go to multi-categories then. So I will try to spend some time on this to get really the intuition of what's going on. But I will skip the definition because, so like I said, multi-categories are just categories, but where the map has multiple inputs. So you have multi-maps in a multi-category, where the domain is a list, finite list of objects, and we represent them graphically in this way. So you have to read things from left to right. So F goes from A1, AN into B. And what is important is that you have a notion of composition. And so this composition will have an identity that is unital, will be associative, and you will also have that composing in different inputs can be done in any order. So the order doesn't matter. We call this the interchange or the exchange law. And so we can actually write things in this way without imposing an order on the composition. Some examples are sets and functions with multiple variables, categories and functors with multiple variables, vector spaces and multilinear maps, as I said before. There is also banner space and short multilinear maps, that are some multilinear maps that are kind of doesn't expand the norm in some sense. And also you can think of abelian groups and multilinear maps, so maps that preserve the group structure in each variable independently, and so on. And the main point is that you can define a tensor product in the same way that you will do in vector space. So the idea is a tensor product of a list is an object that comes with a map that goes from gamma into tensor gamma, and such that any map that has gamma in its input will uniquely factorize through M, followed by a map that has a tensor gamma in its input. So any multilinear map F can be linearized into a map from the tensor product of the input. And this in a unique way. So especially since this map is unique, the tensor product is defined uniquely up to unique isomorphism. So we don't have to talk about a tensor product of a list, but we can talk about the tensor product. And so a multi-category that has all tensor products for any finite list is called representable. And so all the examples that I talked about before are representable in kind of obvious choice. So for sets, it's representable where the tensor product is a product of sets, so Cartesian product. For categories and functors, it's a categorical product, so the Cartesian product of categories. For vector space and multilinear maps, it's the tensor product of vector space. For banner space, it's something that's called the projective tensor product, which is the tensor product equipped with a specific norm. And abelian groups, it's also the tensor product of abelian groups. And we also have this idea that if you give me any model category, I can build a representable multi-category that we call the underlying multi-category. And so it will have the same object as the model category. And a multi-map is just a map that goes from the tensor product of the input into the output. So always keep in mind the idea of vector spaces. So a multilinear map can be defined as a map that goes from the tensor product of the input into the output, and which is linear. And we will see that we can actually go the other way around. And any representable multi-category comes from either the underlying multi-category of a monoidal category. And so we can represent tensor project graphically in this way. So on the left, this is like the map, the multilinear map that goes from A1, AN into its tensor product. So this M map that I talked before. We'll introduce it as a white dot. And we'll introduce this kind of gadget that is, in some sense, a co-multiplication. That is a black dot, and that goes from the tensor project into A1 AN. And you should think of it as divided by M by the multiplication. We'll see why. But one way of thinking of these two things is that this Y dot is the introduction of the tensor project. That goes from A1 AN, and I introduce that tensor product. And the black dot is elimination of tensor product. And so remember that if I give you any map F that has gamma in its input, we can divide it by M to get F divided by M that has tensor project of gamma in its input. And so how do we do that? We just pre-compose by this divided by M map. And this gives us F divided by M. And we want that this factorization property, that F is equal to F divided by M composed with M. And so this is this picture. So to enforce that this is true, we need to add an equation that say that basically using the white thing and then the black one just after, the same as doing nothing. So this means that if I'm introducing a tensor project and then eliminating just after, the same as doing nothing. And so we have an equational theory for this tensor project. So the one that I just said there, introduction followed by elimination, the same as doing nothing. We also have elimination followed by introduction, the same as doing nothing. And so this is saying that M divided by M is the identity, which is true by uniqueness of the factorization. And then we have this kind of rule that say that the Y dot is monoid, or pseudo-monoid. And this comes from the fact that the multiplication map compose. And so basically what is this saying? It's saying that you can get rid of the bracket for the tensor product. So if you have a tensor of tensors, it's the same as taking the tensor of all the elements. And you don't have to care about the order of the tensor. And you also have some comonoid kind of thing for the pseudo-comonoid for the black dot. And so this gives us a way of reasoning about tensor project. And so an example is, so like I said, you can, any monoidal category has an underlying representable multi-category, and you can go the other way around. So if you have a representable multi-category, it's the underlying multi-category of some monoidal category, Rm. And so this monoidal category you get by considering the object to be the object of some multi-category. Morphism, you just restrict to unary maps, so the map that has just one input. The tensor product of an object or an object is just a tensor product of your representable multi-category. Now you want to define the tensor product on maps. And so this is the formula. But so if you look at it graphically, it kind of makes sense. The idea is that I'm starting from the tensor product of the inputs, and I'm eliminating this tensor product to get all these inputs, A1 through AN. Then I'm using my maps to get the output B1 for BM, and then I'm introducing the tensor product again. And so in a similar way, we can define graphically what is alpha, the associator that goes from A tensor B tensor C into A tensor B tensor C. And so you can think of it as kind of rebracketing. So you just eliminate the tensor product to get A, B, and C, and then reintroduce it, but in another order, or the order that you want. And using this graphical notation, you can, for example, prove that the pentagon law holds for this, and it's actually a monoidal category. So this is one side of the pentagon law. This is another side. So I won't go into the details of why, but basically you can use this equational theory to prove that both of them are equal to this thing, and so are equal. And the idea is that every time I have an introduction followed by an elimination, I will remove it. So there, this thing, I remove it, and I just straighten this wire there. And same for all of this. And so this proves that so these things are equal. And what is that? So basically, the idea is that I have A tensor B tensor C tensor G, everything bracketing on the left. I eliminate all the tensor products, and then I reintroduce them, but starting from the right. And so this gives kind of an intuitive way of thinking about what is going on in this model category. So, yeah, if there's any question about multi-categories and this graphical view. Otherwise, I will go to polycategories, and also, of course, interrupt me if you have any question. So instead of going into the details, I will give you polycategories in one picture. So like I said, the idea of polycategories is that you have multiple inputs, but also multiple outputs now for your maps. And you can compose along one specific object. So you cannot compose along multiple objects, just one object. And so if you are a logician, you want to think about the cut rule. Yeah. So it's really mimicking the cut rule. And the idea is that, so examples, so we have polycategories are like functions with multiple inputs and multiple outputs, or vector space with polylinear maps. Well, polylinear maps is, for example, a map that goes from the tensor product of the input into the tensor product of the output. You also have planar space with short polylinear map. I can go into this for lack of time. But so more generally, like for vector space, for any model category, I can define a polycategory. So polymap goes from the tensor of the inputs into the tensor of the outputs. Or more generally, if you know about linearly distributed categories or star-autonomous categories, where you have now two monadal structure, this gives a notion of polycategories, where you go from the tensor product of the inputs into the power of the outputs, or polymaps. And so in any polycategory, we can define this notion of tensor and power. So the tensor is defined in exactly the same way, but for multi-categories. So it's saying I have an object, the tensor, coming with a polymap into the tensor, such that any map that has gamma in its input will uniquely factorize from a map that has a tensor of gamma in its input. And for the power, it's dual. So now you have a map that goes out of the power into gamma, such that any map that has gamma in its output will uniquely factorize from a map that has power gamma in its output. And then you have a notion of left and right dual that are similar to the one in monoidal categories, like for compact close categories, pivotal categories. And so the idea that you have a cup and a cap that comes together with some snake identities. And so a polycategory with all tensor and powers is something as a linearly distributed category. And if it has also all duals, it's something as a star-autonomous category. And you can represent them graphically in this way. So on top, you can see these four things on top equation are the same as for the tensor in multi-categories, and they get to tensor in polycategories. Then you have a dual one for the power, where we reverse the white and black dot. So this white dot is like the W map that goes from the power of gamma into gammas, into all of the output. And this white one is divided by W. And then you have these snake identities for the cup and the cap. So that was polycategories in a nutshell. Any question?
Just a heads up, you have about 5 minutes left for the talk, sorry.
Okay, thanks. So I will keep it short then. So I will also give virtual double categories in one picture. So this represents a two cell in a virtual double category. So virtual double categories, it has objects. It has vertical maps between objects, horizontal maps between objects, and two cells that goes from a list of the horizontal map into a list, to one horizontal map, sorry, along some vertical maps. And so you want that object and vertical maps form a category. You want identity to cell and composition of two cells, but you don't ask for composition of horizontal cells. And so if you have identities and composition of horizontal cells, then any two cells can go from one input, one horizontal input into one output, and you get the notion of double categories. So this is like identities and composition of two cells. So examples are sets, function, and relation with some notion of two cells. You can take categories, functors, and cofunctors or distributors with two cells. So I won't go into the two cells. So you have rings, ring homomorphism, and bimodules, or V categories, V perfunctors, and V perfunctor. And so our idea for the graphical notation is that any multi-categories can be seen as a one object, one vertical map VDC. So if you look at the two cells like that, and if you take just one object and just the identity as vertical maps, then the data is a list of horizontal arrows that you will think of as element of your multi-category. And then for any list of objects, and so objects with multi-category, and for any list of objects and any object source, we get a two map, which is like the multi-map in the multi-category. And so building on this, we can represent two cells in this kind of colored way, where you have the two cells that goes from a list of horizontal map, P1, Pn, into an horizontal map, where the horizontal map goes between objects, A1, A0, A1, A-1, An, and then these vertical maps connect the source and target object. And so you can check that composition actually work well, it's well defined with this convention. And so there you can define the notion of composite that is similar to the notion of tensor project. So basically, if you give me a list of arrows that are in a chain like that, a composite is an arrow that goes from A0 into AN, coming with a two cell along identities that has some unique factorization properties. So it's defined in a similar way as tensor project. And you have that virtual double categories with all composites or equivalent to double categories. And so you can represent them graphically in this way. You just colored everything. And so you don't put vertical arrows for the dot, because if you look at this two cell, it's along identities. You don't have to have vertical arrows. They are just identities. Yeah. And so, yeah, really quickly a functor, because we have time for functors. So we'll say that I have 2 minutes for them. So a functor of polycategories that will represent vertically. And so this is saying that the image of I is AI, the image of phi is F. And so the image of phi goes from the image of its inputs into the image of its outputs. So we'll present this top like that. And so our Cartesian map, it's a unique factorization property. So it's a map from gamma into the tensor product of pi, so into the tensor product of pi along F, so where F is the image of phi, and so such that any map uniquely factors through phi, but only if it's already is factoring in the bottom. So if already the image is factoring, so it's kind of a parameterized notion of factorization. And then a fibration is something where all of this tensor F exists, so we call them push forward. And so I will skip the example, but the idea is that push forward can be thought as parameterized tensor project, as the notation suggests. And in particular, you have this terminal multi-category, and an up fibration with regard to this terminal multi-category is the same as a representable multi-category. So like push forward for this specific functor correspond to tensor project. And so we can define functors graphically, basically by writing. So the thing on top is the thing in the domain, and this is in the codomain. And we will define our Cartesian multimap by also with a white dot, but we will say it's our Cartesian above which thing. So we'll kind of parameterize also the white dot and saying we have this map that goes from A1 AN into tensor F of A1 AN. And we will also parameterize the kind of factorization by so like the black dot from earlier. And so yeah, then we have this fibration graphically where everything is parameterized, and so we need to check for example that when we compose white dot, the thing inside would be the composition of this thing. And also that when we eliminate things, we should have the same map inside. So yeah, that's it. Just to conclude, basically how to combine this idea. So combining bifibration and polycategories is something that I did for most of my thesis, and you can find reference for this in a paper with Noam in NFPS. Then fibration of virtual double categories, it's work in progress, and I've written some of it in my thesis, soon to be out there, I hope. Colored polycategories is work to be done, and I know that other people are thinking about this too. And then, of course, the holy grail will be putting everything together and a bifibration of colored polycategories. So maybe one day. So yeah, thanks for listening to my talk.
All right, thank you. Let's thank the speakers. All right, do we have any questions? Okay, oh no, they are clapping hands, not raised hands. All right, if there are no questions, then we'll take a break. I'll open up some breakout rooms if you want to ask the speakers any questions or just discuss things. Feel free to do so. Yeah, and open. Okay, and we'll be back at 9:30 for the next block. Oh, yeah.